The Baldwin 60,000 was so thermodynamically advanced, it could convert steam to mechanical power at efficiencies conventional locomotives couldn't touch. The problem: it needed so much maintenance that railroads couldn't actually use it. I think this might be the most elegant engineering failure in railroad history. Some people see the turbine locomotive as visionary proof that steam had more runway left. Others see it as Baldwin doubling down on a dying technology while the diesel revolution rolled right past them. By the late 1920s, Baldwin Locomotive Works was staring down an existential crisis. The steam locomotive market was saturating hard. Every railroad that needed power already had it, and replacement cycles were stretching out. Then came the diesel-electric threat creeping in from the margins. Baldwin's executive team had a choice: manage decline or make a technological leap that would redefine steam power entirely. They chose the leap. The directive went out to the engineering division to develop something that would make reciprocating steam look obsolete. Not incremental improvement, but fundamental reinvention. The answer was steam turbines. Why turbines? Because stationary turbine plants and marine applications were already proving that turbines could extract more energy from steam than conventional piston engines ever could. Higher thermal efficiency, smoother power delivery, and dramatically fewer moving parts. No reciprocating rods hammering away. No side-to-side forces trying to tear the locomotive apart at speed. Just continuous rotary motion, converting high-pressure steam directly into wheel torque. Baldwin partnered with Westinghouse Electric, who knew turbines cold from power generation work. The target was ambitious: over 6,000 horsepower for high-speed passenger service, with projected fuel savings of 30% and maintenance intervals that would make conventional power look primitive, but turning a stationary power plant into something that could handle railroad curves, grades, and weather? That was about to get complicated. The turbine itself used a forward turbine for main power and a separate reverse turbine for backing up, which already meant double the complexity. But the real headache was the boiler. Steam turbines need sustained high pressure to work efficiently, around 1,500 psi, versus the 250 to 300 psi conventional locomotives ran. That meant water tube boilers operating at pressures that would make most railroad mechanical departments very nervous. Then came the wheelbase nightmare. The turbine, boiler, and condenser created a rigid frame 122 feet long. You can't negotiate curves with that, so Baldwin divided the whole assembly into 3 articulated units: the engine unit, the tender, and the condenser car. Total weight came in at 856,000 pounds, requiring special track clearances that not every railroad could provide. And here's where it gets messy. Steam turbines need condensers to create the vacuum that makes them efficient in the first place. Stationary plants just pump cooling water from a nearby river. Railroad application meant carrying a massive condenser car with you everywhere, circulating 7,000 gallons of water through radiator sections. The catch? Cooling capacity depended entirely on ambient temperature. Summer operations meant efficiency collapsed exactly when passenger demand peaked. The first unit got delivered to Pennsylvania Railroad in 1926 for testing. Initial trials actually showed promise. The operation was smooth, acceleration was good, and the turbine delivered the kind of effortless power that made conventional locomotives feel crude. But then the maintenance intervals started coming in, and they were insane compared to conventional power. Turbine blades eroded from impurities in the steam that wouldn't have bothered a piston engine. Bearings failed from constant thermal cycling as the turbine heated and cooled. Baldwin went back to the drawing board. They added water treatment systems, improved blade metallurgy, and revised bearing designs. Each solution added weight, complexity, and cost. So by the time Baldwin had something that actually worked reliably, they'd basically built a locomotive that needed a dedicated maintenance crew following it around. Despite the testing headaches, Baldwin committed to production anyway. 3 different railroads ordered units: Pennsylvania, Chesapeake and Ohio, and Norfolk and Western. Total production ran to about 12 units, built between 1926 and 1930. Price point was roughly $250,000 per locomotive versus $150,000 for conventional passenger power. The pitch was that fuel savings and reduced maintenance would offset the initial cost. Baldwin was selling a promise the engineering couldn't actually keep. Here's what railroads actually wanted in the late 1920s: reliability over efficiency. They needed scheduled maintenance windows, not unexpected failures. They needed interchangeability, so power could swap routes and assignments freely. The 60s' fatal flaw was being too specialized. It couldn't fill in anywhere. A conventional Pacific or Hudson could be maintained by any shop crew with standard tools and skills. The turbine required specialists, special tools, and expensive replacement parts that had 6 to 8 week lead times. Operating range was limited because the condenser car meant fixed water stops. You couldn't deviate routes. Pennsylvania Railroad assigned their turbine to the Chicago to New York City run. There was initial excitement about the smooth ride and impressive acceleration. Then reality set in. Turbine blade failures started showing up every 30 to 40,000 miles. Conventional locomotives were going 150,000 miles or more between major overhauls. Maintenance costs spiraled because specialized parts had 6 to 8 week lead times. Availability rates were catastrophic. The 60,000 spent more time in shops than on the road. Any problem with the condenser car meant the entire locomotive went offline. There's a specific incident where a blade failure happened in Fort Wayne, and the locomotive sat sidelined for 3 months, waiting for parts and repairs. Summer heat destroyed condenser efficiency completely. On Chicago summer days, the condenser struggled to maintain adequate vacuum. Performance degraded by 20 to 30% in hot weather, which meant slower schedules exactly when passenger loads were highest. Winter presented the opposite problem: freeze protection for the condenser system. The solution was adding a steam heating system for the condenser car, which meant burning coal just to keep the cooling system from freezing. The absurdity of it: using fuel without producing any work. Engine men hated it. Turbine operation required a completely different skill set from conventional locomotives. There was no throttle position feedback like they were used to. Speed control was imprecise, and it was easy to overspeed the turbine, which caused catastrophic failures. The reverse turbine was awkward to operate, with limited backing capability. Shop crews needed specialized training. Most mechanics couldn't work on it at all. Parts inventory for 1 or 2 unique locomotives made no economic sense. Union resistance built up because crews preferred familiar conventional power. The sentiment from the shop floors was basically this: it was like asking a blacksmith to repair a wristwatch. While Baldwin was wrestling with turbine problems, railroads were buying conventional steam by the hundreds. Pennsylvania's K4S Pacific had 350 units in service, providing reliable 100-mile-per-hour passenger runs maintainable at any division point. Operating costs ran about 85 cents per mile versus the 60,000s estimated, $1.40 or more. Maintenance intervals meant K4S locomotives could run for months between shop visits. The real killer was standardization. Interchangeable parts across the entire fleet meant any crew could service them anywhere. New York Central's Hudson told the same story. 275 units, proven technology, economies of scale, working exactly as intended. Meanwhile, diesel electrics were creeping in from the edges. By 1935, diesel switchers had proven themselves in yard service. EMC's Zephyr Streamliner from 1934 showed what passenger diesels could do. The advantages were stacking up fast: no water stops, multiple unit capability, fuel efficiency, competitive with turbines on paper, but vastly better in practice. Maintenance intervals measured in months instead of weeks. When you line up the comparison, the turbine loses every single argument. Efficiency advantage only showed up at sustained high speed. Reliability couldn't match decades of proven conventional steam. Maintenance required specialists and exotic parts. Operational flexibility was non-existent compared to conventional or diesel power that could go anywhere. The economic case collapsed when fuel savings got erased by maintenance costs and terrible availability. The 60,000 won the engineering contest, but lost every argument that mattered to a railroad trying to make money. Most turbine units got retired between 1935 and 1938. Total service lives barely reached 10 years for most of them. Conventional locomotives often ran 40 years or more. Pennsylvania's last turbine limped along until 1949, but it only saw sporadic use after 1940. The production numbers tell the whole story. 12 turbines built versus thousands of conventional engines rolling out of Baldwin's works during the same period. Final disposition was straightforward. They got scrapped. Some turbines were salvaged for stationary power plant use, which is where they probably should have stayed in the first place. Baldwin never recovered the development costs. The financial hit contributed to the company's long decline through the diesel era. So here's what Baldwin should have done. They had engine building expertise. They understood precision manufacturing. They could have competed with EMC and ALCO in the diesel-electric market if they'd committed early. Instead, they pursued a steam turbine dead end while the market shifted underneath them. The strategic error was mistaking technical sophistication for market need. One lever could have changed everything: honest operational testing before production commitment. If Baldwin had run those first units for a full year and actually listened to what the numbers were saying, they would have seen the cooling problems, the maintenance nightmares, and the operational inflexibility before committing to production. They could have pivoted to diesel research in 1928 or 1929 with enough runway to matter. By 1940, Baldwin was playing desperate catch-up in the diesel market. They never recovered that lost decade. The central lesson here is that railroad technology has to be operationally practical first and efficient second. The turbine prioritized thermal efficiency over everything else, but railroads needed reliability, maintainability, flexibility, and reasonable costs. The 60,000 delivered none of these despite being thermodynamically superior to anything else on rails. Technology that requires specialists fails in generalist environments. That's the human factors problem nobody wanted to acknowledge. Compare the turbine to actually successful railroad innovations like air brakes or automatic couplers. Those solved real operational problems that crews and railroads faced every day. The turbine solved a theoretical fuel efficiency problem that didn't justify its operational costs. Advanced doesn't mean useful. That's what the 60,000 proves beyond any doubt. You can engineer something that's technically brilliant and operationally useless at the same time. The turbine was a magnificent machine in isolation. Smooth, powerful, efficient under ideal conditions. But railroads don't operate under ideal conditions. They operate in the real world, where things break, where schedules matter, where maintenance has to happen in division points across the country with whatever crew and tools are available. I still think this is one of the most elegant machines ever built for railroads. There's something genuinely beautiful about the engineering ambition behind it. But that's exactly what makes it tragic. All that brilliance in service of the wrong goal. The 60,000 sits in history as a cautionary tale about innovation that ignores operational reality. The image that sticks is this: a magnificent locomotive sitting idle in a maintenance shop, too complex to use, too expensive to fix, and too specialized to matter. Baldwin built the future, but the future nobody actually needed. I'd love to hear your thoughts. Please leave a comment below and give this video a like if you enjoyed it. See you on the next one.